All right. Let's get started. Hello, everyone. Welcome to ML4EU Showcase event number 2. I'm Tarun, the coordinator for this community of practice. ML4EU is an ARDC initiative to accelerate machine learning based discovery, while this community of practice is co-facilitated by ARDC and Monash Data Science and AI platform. The first showcase event witnessed 6 research projects on the theme of ML in imaging. In today's showcase event, we will look at 6 more interesting projects on the theme of system monitoring and forecasting. Mrk Crowe, who is a skills development manager at QCIF, will be chairing this event. Without wasting any more time, I'll hand it over to Mark. Over to you, Mark.
Great, thank you, Taryn. Can everyone hear me, hopefully? Yep, good. All right, so yes, as Taryn said, yeah, we've got a big schedule this afternoon. We have a total of 6 speakers, and the plan we'll do is we'll have 3 speakers, each giving their presentation, and then a sort of a 15-minute break or so after that, where we can discuss those topics in a bit more detail and answer some questions at that point. We will try and have time for 1 or 2 questions after each talk if they come up, but we do have quite a busy schedule, so we will try and keep things moving on this afternoon. The speakers, please, if I could get you, if you have got a timer, you can look at yourself. That will save me interrupting you, but I will try and give you a warning after 10 minutes so we can wrap those up in about 12 minutes and have time for 1 or 2 questions. Also, in the interest of time, can I suggest that we put questions into the chat rather than asking them after talks? That will give us a little bit more time to look at the questions, and also means that if we don't have time to answer them all at that particular point, we've got them sort of recorded for those break times in between. So I see Taryn's put the list link in the chat for the abstracts and bios, so I am not going to waste time on rereading all of those. They are there for you to have a look at as you like. But without any further ado, I will get things underway and invite Ryan Hartshorne, who is going to be our first speaker, who's going to be talking about learning to run a power network. So Ryan, if you have a presentation you're ready to share, I will hand over to you as soon as you're good to go.
Cool.
Excellent.
All right.
Thanks you very much.
Can everyone see the screen and hear me?
Yes, we can. Thanks.
Great. All right. Hi, everyone. So my name's Ryan, and I'm the lead for the Learning to Run a Power Network project. So our team is a bit of a hybrid research competition team. And what I mean by this is that we aim to compete in the ICAPS 2021 Learn to Run Power Network competition. However, if we achieve promising results, we have the opportunity to present at the international conference and submit a conference paper. It's also worth noting that our team only formed together a month and a half ago, so we're still very early in the exploratory phase of the project. So before we dive into the project, I should acknowledge everyone in our team and mention that our project is a collaboration between the student team I represent, Monash Deep Neuron, which, for those who don't know, is a student-run team at Monash that houses research projects for students to participate in deep learning. And we also collaborate with the Monash Department of Data Science. Cool. So before we dive into the competition, I'm just going to quickly talk about power grids. So I'm sure everyone's aware. Power networks in our modern society are increasingly more and more important as they are the backbone to our modern society. Power grids run on the idea of supply and demand, so there must always be a balance. As the competition states, decarbonization, decentralization, and digitization is changing the way we operate our power grids. And as we introduce new renewable sources of energy, the grid has become ever more complex to operate. And now there are certain other conditions that must be met to ensure maximum efficiency. So for example, we have solar panels now. So like on a super overcast day, we might not be able to operate them as efficiently. We have to counteract for that. So grids always also have to adjust for scheduled maintenance work. So if a subset of the lines are offline, how do you rearrange the grid elements to be able to handle this? So also, key point in power grids is that failure is not an option. So failure to keep this balance within the grid may cause blackouts, and blackouts unfortunately have significant life-threatening consequences throughout the population. Another challenge that power grids face in our modern world is the threat of adversarial attacks. So after multiple attacks on utilities like the Colonial Pipeline attack in the US, power grids must be able to handle potential attacks that cause unexpected line disconnects and failures. So the L2RPN competition is run by 3 research institutes around the world. And it's being hosted this year by the ICAPS 2021 conference. So the aim of the competition is to determine if artificial intelligence could one day be used to assist in the operation of a power grid and to be able to tackle the challenges that I've previously mentioned. So the competition was recently started in 2019. It's built quite a steady following, and last year's competition had housed 5,500 participating teams. So the original grid was very small with only like 14 substations in the network, no dynamic events, and it's built up to medium and large scale grids over the last year with multiple environments, multiple different types of actions you can take in that environment. So like you can disconnect and reconnect lines within a substation, rearrange the bus configuration. There's also redispatching of generators and that kind of thing. You don't have to worry too much about the technical details, but there's a lot to manipulate within a power grid to get it operating efficiently. So last year's focus was about robustness, and this year they're focusing really hard on this idea of trust and how can we have this kind of safety within the operation of the agent. So when we started, like the question for our team was, can we define this as a reinforcement learning problem? So half our team is built up, or 3/4 of our team is has a background in deep reinforcement learning. And we've also got 2 members who are more of optimization people. So first we decided to define this in an MDP, like a Markov decision process, which is essentially like a stochastic control process that provides us with a framework for modeling decision-making. And it must also follow the Markov property. So what I mean by this is we have this Markov property, which states that the future is independent of the past given the present. So if we have our state given in this example on the left, at any point in time t, if we apply an action to it, we should be able to find the probability of the next state without any knowledge of the prior states. So we don't need a history of everything that's happened to be able to determine this probability. In this environment, what helps us is that we know that a power network is governed by the laws of physics. And as the competition states that actions are implemented after every 5 minutes, we have this discretized time. So we can assume that the Markov property holds. We can also define a reward function based on duration of time without a blackout and penalize heavily for a blackout, giving us our full MDP. So as we have previously stated, power networks are governed by the laws of physics. And this means that we can simulate the grid and how our agents will affect it. So the L2RPN competition provides an environment to simulate a countrywide IEEE 118 bus system grid. Essentially means that each substation has 2 bus bars and we can rearrange the elements. So on each substation, we will have we'll have a load or some form of a load, like a few generators and a few different lines. And we can change the configuration of this between like not on a bus bar, on bus bar 1 or bus bar 2. And at any point in time, we can only do one action, but this action is a concurrent action, which means that you can only target one specific bus station at each point in time. But within that bus station, you can do as many configuration changes as you want. So thankfully, we don't have to write this environment ourselves. Competition gives us also this visualizer, which you can see, where we can load in simulations that our agent is trained on and play them out to see how they performed. So naturally, once we had defined the problem, we ran some baseline reinforcement learning algorithms from the Q-learning family and found that we could get results even from the most primitive Q-learning methods and algorithms. However, we hadn't addressed the main theme of this competition, which was trust. So up to this point, we had just been addressing the environment as somewhat of a black box without actually considering our constraints in detail. And what I mean by this is that we haven't we've just been learning off of the constraints already placed in the environment through the reward system, which the competition has defined. However, we haven't actually addressed the fact that the operation of a power network can lead to these life-threatening situations. So we need to have some sort of a robust solution to be able to ensure that the maximum return is governed by not failing. That was a very simple way of putting it. So we went back and we redefined these constraints, and we just said, okay, we cannot fail. That's not an option within our network. And the competition, as part of this year's competition, they've given us the action to raise an alarm. So if we believe that an area of the network is in trouble, we can raise this alarm and alert the area that there will be a failure, and we get somewhat of a reward for that. So there are also physical constraints within the network, so thermal line limits. We have like a voltage range which we can operate in. We also have this constraint that generation and loads must be balanced at all time. We also have this cost kind of constraint. So there's a cost of ramping up and ramping down generators, turning on generators as well. And there's also a cost that comes with raising an alarm if there is a blackout. We've also got this constraint, which is that we can only take that one action within the environment. So we can only manipulate one substation at a time. So this might mean that in the future, we want to configure like 6 different substations. However, if we can only do an action every 5 minutes, it's going to take quite a long time. It's going to take 30 minutes at least. And we've also got this issue of different energy sources. So we've got like nuclear, solar panels, wind, and regular coal generators and that kind of thing. So what we have delved into is this kind of subfield of reinforcement learning known as safe reinforcement learning, which can be described similarly to traditional reinforcement learning, where you're trying to maximize your expected returns through your actions. However, in safe reinforcement learning, we're actually trying to maximize this expected return while avoiding catastrophic failure, essentially. So what we can do is describe this problem with a constrained Markov decision process, which incorporates in that MDP tuple a set of constraints, which we can define, and we can define our expected return to be subject to our constrained criterion. So what we are saying is that each constraint must fulfill some sort of condition, and each reward must fulfill some sort of condition. And we have this kind of like function related to the return and like some threshold restriction values. And this, we can visualize it to make it much more easier to understand. Essentially, you're saying if we've got this policy space, which our policy is like the behavior of our agent, if we don't have any constraints, it's like this huge kind of circle, as we can see here. But our actual allowable policy space, where we really want our optimal policy to be, is within a much more, it's a subset of this policy space. So we're trying to get this safe, allowable policy.
Ryan, you're coming towards the end of your time. If you're nearly finished, that would be great. Thank you.
About to wrap up. So our base kind of agent, our proposed agent, is this soft actor critic, which we're going to manipulate. And this is housed in a model-free policy gradient algorithm, as a model-free policy algorithm. And so it works by modifying the policy directly as opposed to Q-learning, which will approximate this like Q value, this state action pair value. So I'm not going to go into distributional reinforcement learning due to time. However, just quickly to discuss how we're tackling this alarm system, what we're going to do is somehow have this uncertainty variable. And if this uncertainty factor reaches a certain point, we'll run through like a tree search to kind of understand how many potential states in the future from where we are now will lead to a blackout. And if we meet this kind of criteria of how like a certain amount of states will be blackouts, then we will determine to raise the alarm in a certain area. Thank you very much for listening.
Excellent. Thank you, Ryan. Thank you for finishing up nice and on time. We do have a question in the chat there from Pascal, curious about the flexibility in the environment and fudge factors. I'll let you read it yourself rather than read it to you.
Yeah, sorry. I'm just having a read of it now. Team of developing nations which have complex and not well documented grids. Yeah, so this is a problem that we're faced in the team as well, because initially when we tackled the problem, we wanted to have this very generalized algorithm. And we wanted to, be able to solve the problem where if people are just adding loads on constantly, because a grid isn't going to be static, it's going to be over time, you're going to have new generators, new loads, constantly, it's going to be changing. So how you deal with this kind of grid, unfortunately, the competition hasn't gotten to the stage where we will be tackling this problem. But I hope for the competition in the future that it will get to the stage where we will have this dynamic grid. And we have to go, well, how do we solve this problem now where we're not just learning like how to deal in this environment, how do we deal in multiple different environments?
Cool. All right.
That answers it.
Excellent, thank you. And there's another question there from Ming Fu. We've got a minute or two left. So if you think you can answer any or all of that in that time, go for it.
Okay. So the difference between this kind of problem and a traditional deep learning problem is that we don't particularly have like a discrete size for our data set. So because we have this environment that we can train on, we can afford to be sample inefficient, and we can actually afford to just learn off continually beating the crap out of our agent and learning from this environment essentially. So when we run our simulations, there's no limit. It can be an infinitely sized data set. However, there is a constraint when it comes to running the agent in the competition. There is like a certain amount of resources that we're given, and it must be able to perform, or it must be able to operate the grid in a calendar year in 30 minutes.
Excellent. Thank you very much for that. That's excellent. A lot of great work there, and really interesting sounding project. Looks like you're up against some stiff competition with 5,500 people, but good luck. Okay, so thank you everybody. And as I said, there'll be time to come back and talk to Ryan further in our longer break in the middle. But now I'd like to introduce our next speaker, Endrei, who, when we are allowed back on campus, is actually in the office just down the corridor from me, but haven't seen him for ages because we haven't been on campus for ages. Anyway, so Mark is going to be talking about predicting optimal OpenMP directive configurations for HPC. So if I can get rid of that noise in the background, Mark, over to you to give your presentation whenever you are ready.
Thanks, Mark. So let me share my screen.
Please do. Okay, that's come through. That's coming through now. Yep, we're good to go.
Okay, and if I put in slideshow mode. All right, so yeah, this project is about predicting optimal OpenMP directives for high-performance computing applications, and it's a collaboration between the UQ Research Computing Centre, where I'm a software engineer, and the Livermore Labs, as well as Cray. So a bit of background on the problem and the research question we're trying to address. So it can be quite challenging to parallelize programs that we want to run on HPC systems because you can have highly nested constructs like loops with lots of independencies. Complex hardware configurations underneath it, you've got to optimize the parallelization for as well. And then added on top of that, if you want to move to another platform, often you have to redo it all again because of differences with the underlying hardware and operating system and so on. So our goal with the research is to see if we can use machine learning models to predict parallel programming constructs that provide a significant benefit performance-wise over default settings that we would get out of the compiler automatically. So the way we've approached the problem is to adopt a suite of OpenMP kernels and use them as a case study. So they've got various functions built into them that they simulate, I guess, for typical things that scientific applications do. And we then want to identify a bunch of parallelization directives or pragmas that we can use in the compiler that have the same functionality but different performance characteristics. So they won't affect the way that the algorithm works, but they'll affect the way that it performs. So we want to collect a bunch of performance data for each of those configurations and kernels, and then train a model, a classifier model, to see if we can predict an optimal configuration. So some of the techniques that we've applied are around sample data preparation. I'll talk a little bit about scaling in a minute. On encoding, when we're using pragma constructs that are just text keywords or kernel names, we need to convert those to numerical values so we can train the model, and there are a few different approaches. We've looked at ordinal, which is just turning them into a number sequence, or one hot, where you've got a list of bits that are true or false that you're providing as inputs for the model. And we've really found that didn't make a lot of difference in our case. Ordering of the data has been important for us. Like when you're training or collecting the sample data, you're doing it in an order of kernels, and if you feed that into the model in the same order, the model does work quite well. But then if you want to split data out for validation or whatever, you're going to be taking a big chunk of data for a set of kernels that's going to be missing from the training. So if we randomize the data first, it's best practice for a few reasons, but the main driver for us is that we're not pulling our validation data just from a small set of kernels that affects the training. We looked at classification versus regressor approaches, and we did some previous work with a regressor that worked quite well, where we were just using a small number of samples to curve fit. But what we want to do in this case is get a large number of samples and then be able to give it one more sample that the model can classify for us with an optimal pragma configuration. Our network layout has been pretty standard. Like, we started out with a pretty basic single hidden layer network, and have tried different configurations, but the single layer model seems to work fine for us. And then model validation has been important as well, so I'll talk about that a bit more in a minute. To give you a bit of an idea of the optimization search space we're dealing with, so we've got this suite of OpenMP kernels I mentioned. There's 62 of them from DAXFit, a 3D volume calculation. We focused on the OMP parallel for pragma, which is the directive we're using to parallelize a for loop, and then looked at a number of clauses on that deal with how many threads you're using and how the threads are placed on the hardware, and vector operation sizing and so on. And we end up with 62 kernels by around 240 clause combinations, which gives us a total of nearly 15,000 samples that we're feeding into the model. Looking at the data a little bit more closely, a couple of issues we ran into was measurement error. So when you're instrumenting an application on an HPC system, there's some overheads of collecting the instrumentation data. And if you can keep the runtime high compared to that sampling overhead for measurement data, it's going to reduce the perturb the application less. So that's one important thing we're doing, is keeping the runtime high compared to that. And the other thing is, we could collect all the samples in one run, but we've decided to split them across 3 runs. So if you're collecting too many samples in one run, that increases your overheads as well. And that gives us the added advantage that we've got 3 different runtimes for the same 3 samples. And we can use those to flag where we're getting deltas in the runtimes that shouldn't be there. We used Pearson data correlation to try and understand what some of the relationships in our data were. And I guess one point with the correlation plot is it's probably not all that helpful for our categorical data like the pragma classes or the minimal pragma class, which is our label. But the thing we're ultimately aiming to optimize is the runtime, and we're seeing some useful correlation information for the runtime, particularly around things that aren't that helpful, like things that are zero or very low correlation. For example, runtime, we've got floating point arithmetic, single precision, very low. So, maybe that's one we could drop because our kernels are all double precision. Another one that's quite high is the resource, is the total CPU cycles. And really that's just a proxy for the overall runtime. So we could probably drop that too when we're optimizing the model at some point. Model convergence, I mentioned, so early on in the work, we were finding we were getting quite a bit of variability and not all that great results. And by looking at the model convergence with, plotting the history we're getting back from each iteration, we were somewhere down here early on. And so there was more work to do with fit. So increasing the iterations and actually taking out some data from the sample data for model validation gave us a level of comfort that we did need significantly more epochs in the training, and that we weren't overfitting. We weren't seeing this bounce around in where it was leveling off nicely at around 1,000 epochs and getting up high near 100%. We found that the best trade-off, like pulling data out for validation means we've got less for training. So the best split for us was 80% for training and 20% for validation. So some of the challenges we faced included some of the compilers are very good, especially at some of the kernels. They've got optimizations built into them to help parallelize them when you just put on a standard parallelization tag. But so that kind of threw us off a little bit. But then we did find, looking deeper, that there are lots of cases where the compilers aren't that smart and that you can provide good benefits. In some cases, we had default settings that were very good as well. Like either the compiler was configured with good defaults or the operating system or the OpenMP runtime. But then there are other cases where they're not. So, while 70% of cases may be good, there's still 30% that you can get some good value from. I already talked a bit about the measurement error, so I won't go over that again. So there's a lot to digest with this picture, but it's basically showing that for each of our 60 kernels, I've got a little plot. So for DAXP here up the top left, this is showing on the x-axis each of our 240 pragma classes, along with a true value with the blue triangle, and then a bar indicating the probability of prediction by the model. So we've used all the other kernels, all 59 or whatever other kernels, to do the prediction for DAXP, and it's come up with a good result on the true value and high confidence level as well. So the pink colour there means it's within 2%. Well, that's spot on in that case. But if you look across a few of them, it's not always the case. Like the stencil one for here, for example, we've got the true value much lower down than the one the model's predicted, but it's still within 2%. So that's showing us that for stencil, there's a lot of good options, and the models converge on one that's a little bit away from the true one, but still a good one. We've got a red one over here too, which is indicating a hole in the training data. So, that means we should be looking at adding another kernel or something that will help the model lock into the signature of that particular case. Sometimes we've got more than one prediction too with similar probability levels. And that's because we've had a different prediction for depending on which sample we use to train the model for that particular kernel. So, you know, a lot of cases, it doesn't matter which sample we use, we're still getting the same prediction, but for some of them it does matter. So now the aim is that we can find one good sample that'll do the same prediction consistently across all the kernels. So as far as future directions goes, if things keep panning out the way we're hoping they will, there seems to be some quite good opportunities for future work. At the moment, we're looking at pulling in a real application rather than just these small software kernels. We're also looking at other compilers. We've focused on the Intel one so far, but GNU and Cray all have compilers that are widely used. Hardware-wise, hardware accelerators add another layer of complexity. So particularly around vector processing, we'd expect some bigger benefits there too. And then we started with OpenMP, as I mentioned, but there are lots of other frameworks. And another useful thing is being able to translate between frameworks too. So a compiler doesn't necessarily have to support each of the frameworks. If you can translate from one to the other and get an optimal translation, that's a good result. Okay, so that was all I had. Thank you.
Excellent. Thank you, Mark. And yeah, perfectly on time for one or two quick questions. If there is anyone who has anything they'd like to ask Mark about that one. A lot to absorb in that presentation. So maybe when we come back to in the break, but we've got a minute or so in the schedule if there are any quick ones. No, I don't see anyone coming up with that one. So thank you very much for that, Mark. Yeah.
Right, thank you.
Yeah, so look, a lot of interesting work there, and obviously some real world applications when you get things a bit more refined with that one. Okay, so our final speaker for this session is Ziv Hameiri, who is going to, I hope I've got that, pronounce your name more or less right, Ziv. And Ziv will be speaking to you, as you can see there, on advanced analytics and machine learning approaches for photovoltaic applications. So Ziv is all ready to go.
I'm a bit new for...
there we are, good.
Can you hear me?
Yes, we can, yep, so all over to you, Ziv, thank you.
Okay, thank you, Mark, and thank you, Jingo, for the invitation. My name is Ziv, I'm from UNSW. I think that this presentation will be a bit different compared to the other two. My background is not computer, it's PV engineering. So I will explain a bit more on why we want to use machine learning, but less about how we use that. But if there is a question about how, I will be happy to answer after that. So, oops. So how or why? I think that, so the United Nations released just last week the report about climate change. And I think that everyone that read that was quite depressed like me. So I just copy here the part on Australia. And as you can see, it doesn't look good. Temperature will increase, a lot of extreme weather condition, floods, fires. So the future doesn't look so promising. And it's looked like very hard for us to try to beat or to change that. But if there is any hope, the hope will come from photovoltaic, from PV. So just to show you a bit about the market and UNSW position in that, and then we will start to explain what we try to do with our project. So what I show here is something that's called learning curve, and that's something that you can see that for different industry. In this one is of course for PV, and what we show here is the price for power using American dollars as function of how much we produce. And you can see that for PV, this curve is quite steep, meaning that we learn quite fast. Definitely when we compare ourselves to other technologies. So just because we don't have here, we look on how much we produce. This one is 2005. So that's when I started my PhD. It's not that I take claim on this improvement in the slope, but that's what happened. Yeah, we cannot argue with data. But as you can see, we learn quite fast. And the prediction here is that we will reach 10 cents when we will reach 2 terawatt. And the question when we will reach that, if there was more time, I will ask you to guess, but we don't have. So let's look on when we're going to do that. So that's the annual capacity installation in PV. And as you can see, we grow very fast. The truth is that that's one of the faster market for any application. And you can see that we will probably reach the 2 terawatt in 2026. Yeah? Probably in 2 years, we will reach the 1 terawatt per year. And then very fast after that, we will reach that. So that means that this goal of very low price is very soon. And the truth is that it's already exists. So before that, I spoke about power. This time now we look on the price of electricity. And that's, you can see different prices for large installation recently in the world. PV is with red, and you can see the other technologies. So wind is in blue, gas, coal, hydro. And what you can see is that the price of PV is already the cheapest in the world. And there was a report just a few months ago that indicated that PV is the cheapest form of energy today in the world. Not only today, it's apparently in the human history. So we reach 1 cent for kilowatt hour, and that's extremely low. And that's how PV looks like, PV field look today. Yeah? So it's huge area with millions of modules, and each modules, as we will see very soon, is made by quite a few solar cells. So that's the market. Now, just to highlight what is UNSW position in this market. So what I show here is the market share in percentage of different PV technologies. And it's less important exactly what is the technology, but I just want you to look on this orange one. It's technology that called PERT, a lot of P's, but that's technology that was developed at UNSW. And as you can see, in 2022, 80%, it's predicted that 80% will be based on this technology. This prediction is from 2020, yeah? And the truth is that it's wrong because we have 90% of the market. So 90% of the solar cells, the global solar cells in the world, is based on technology that was developed here in Australia at UNSW. And that's quite amazing. Try to think about any other technology that 90% of that was developed in university and in Australia in this case. So we have 2 facilities here at UNSW. We have our lab, but we have also mini production line, and that's helped us to transfer our development from our labs here to production line, and then it's moved to industry. And I'm especially proud to show this roof because this roof is based on technology that I was developing during my PhD, and it's something that's called laser doped solar cells. Back then, that was the highest efficiency solar cells in the market. So that's UNSW and PV. So to make sure that we produce something that is good and lasts for 25 years, because that's the warranty that we give in PV, we need good inspections. So the standard way to inspect solar cells is based on measurement that's called current voltage. And as it say, we measure the current as function of voltage. And that's the most common one. We measure every cell that we produce with this technology. And just as a number, it's more than 30 billion solar cells per year based on the today capacity. As you saw before, it's increased much faster. So we speak about large amount of solar cells. And what we measure the voltage, the current, something that we call fill factor and the efficiency. And why we do that? We do that because we need to filter out the one that doesn't perform well, but we also need to bin the solar cells. So solar cells are made to modules, and that's the modules that you see on the rooftop, for example, in Australia. And usually we have 72 of them in one panel. Now, to make sure, because they are connected in series, we need to make sure that they are very similar in the performance. So what we do, we bin them according to quality, and that's one part of the reason that we use current voltage measurement. And as you can see here in the zoom in, to measure that, we need to touch them. So we need to contact the solar cells. And we'll speak very soon why this one is a limitation. Another method that we use is something that's called luminescence images. Luminescence is just emission without change of temperature. That's the scientific definition. You can think about that a bit like X-ray for people. So that's luminescence image of solar cell, and the dark area indicate problem, while the bright area indicate high quality. So it's a bit like, again, like X-ray. It's not exactly correct because this one is, we illuminate with one wavelength and detect something else, but you can think about that a bit like X-ray for solar cell. And this technology, by the way, also was developed here at UNSW in 2005. So our question in this project of machine learning is, can we replace IV measurement with just images? Can we just take image of solar cell and get all the information that everyone else in the world need IV measurement for? And why we want to do that? We want to do that because, as we saw before, IV measurement need to touch the solar cells, they need contact. So they mean that they can break the cell. We often change the size of the wafer and we change the design, and that means that we always need to change the probing. We aim to measure much more cells per hour, but IV measurement is quite fundamentally limited to lower number. And we're going to have more solar cells with different structures, and that means that we will need more and more IV testers, and that's quite expensive. Luminescence images from either side, as we saw before, it's quite useful and quite powerful. It's already have quite good present in production line, and it's expected to have in almost every production line very soon. It can measure much faster because it's just to take image. It's less restrict, so in some of them you don't really need to contact the cell. And it can provide other information, not only the measurement, because it's image. So the question was, can we challenge what everyone else in the world is doing? Because IV is such a fundamental part of PV technologies. Can we just do that with images? And like Barack Obama said, yes, we can. Yeah. So the way that we try to do that is we collect from our partners in industry quite a lot of pairs. In this study, I show you 20,000. And what we ask the partners to give us the image that they collect and the IV parameters that they collect. So now we have pair of image with the IV data that it's all the parameters that usually or always collect with IV tester. And what we decided is that everything below some kind of efficiency, that's what we will call reject. And everything else we will split according to quality, according to bins. And now I start to use terms of machine learning that you know much better than me. We use CNN, and what we train the algorithm to predict or to detect the rejected cells. And then, of course, we split it to train and validation. So a bit of our result, we found that we can detect quite well the rejected cell. However, our accuracy per bin was not too high, but the promising one was that when we had mistake, it was small mistake. It means that instead of the correct bin, we put it in bin that is a bit, it's one above or one below. But our starting point was much more smaller bins compared to the industry. So we felt that that's not too bad, but we wonder if we can do that a bit better. That's a bit of comparison between different algorithms that we use and the one that we develop. And we found that our one, the one that we develop, is a bit better. So then we thought, okay, maybe we need to do that as a 2 steps. Maybe part of the problem is that the rejected cell is wide variety of cell, from one that really doesn't work to one that almost work. So maybe we just need first to detect all the rejected one and then just focus on the one that predict and try to improve the binning of these cells. So we changed a bit the CNN, and we use we changed the last layer to make it as a feature extractor. And now we try to use regressor to have to bin the cells in a bit better way. So our structure now is a bit different, and we have like the validation test divided to 2, one for the rejected cell and one to the correct binning.
If we are coming towards the end of time, if you can wind it up in a minute or 2, please. Thank you.
Okay. So that's our result. And what we do here, we compare between the predicted efficiency to the actual one. You can see that most of them line well. The color code is also indicating which bins they are. So blue and green is quite makes sense, or it's quite okay. I will just jump on this one. The most important, like we said before, is for the companies to not lose power, meaning that they're binning them and they don't have one cell that push the other one down. So the way that we test that is randomly select cells according to the 2 different binning and compare between them. And I will just do that fast. The conclusion was that you can see that the difference between binning traditionally to the binning that we suggest is almost identical, meaning that just with taking image of solar cell, you can get all the information that usually you need IV tester for. We also tried that on new structure that we didn't use before. So 9 busbar just mean that it's new design. And you can see that either transfer or by fine tuning, we get very similar result, meaning that it's very easy to change the method and use it for other solar cell structures. I will jump on this one, or do we have time? We don't.
Sorry, not really, unless you've got a very, very quick final comment.
Okay, so I will just run to the final comment.
Thank you.
If you want more details, just contact me on this one, but I will just go to the conclusion. The main message that I want you to take is PV is energy source of the present, is not of the future. And we can do PV much better with machine learning. And we will be very happy here at UNSW to collaborate with you. We have a lot of knowledge on the PV. We have also a group here on machine learning with machine learning background, but we will be very happy to collaborate with other Australian group on how to make PV better. That's it, Mark.
Excellent. Thank you very much, Liv. Thank you for bringing it to a halt quickly like that. Is there any quick questions for Liv before we move on? Because what we're going to do now is we're going to have a 10 or 15 minutes to discussion session where we can kind of go back to any of the 3 talks and ask our speakers about anything else that's come up in the meantime, and really just have a general discussion about any other topics that are relevant for today. But what I would like to suggest is that while you all think about your questions and what you'd like to talk about, we take 90 seconds to get away from our computers and have a walk around. So we'll do that now. And if we can reconvene in 90 seconds time, we will get onto our discussion session then. Okay, thanks everyone.
The link for the form came through. The link for the form came through.
Okay, hopefully a few of you are back. I'll make that 90 seconds. So as soon as everyone else returns, and maybe a few of you like to pop your cameras on so we can see who's around, we will get our discussion going again. So thank you very much to all our speakers. Some fascinating examples there of real world applications of what we're all trying to achieve with machine learning. So yeah, I would just open the floor up now to anyone who has any questions for any of the speakers or anything else related to that they would like to have a chat about with their colleagues for the next 10 or 15 minutes. Who would like to go first? All silent there. Have we got our speakers back? We've got Ryan and Mark. Ziv seems still seem to be missing in action. So. Okay, Taryn, what do we normally talk about at these sessions? Because I have to admit I wasn't at the last one, so I don't know what the discussion in the middle is normally encompasses.
In the first showcase, I think we had a lot of questions.
Right. So
I mean, I think we can probably move on to the next set, and then
yeah, I don't want to.
This later on, yeah.
I don't want to rush on if anyone has things I want to ask, but no. Yeah, go. In fact,
I have a very silly question for
Yeah,
Ziv. How is that image is taken, and how do you collect those images?
Okay, so luminescence images based on the fact that we illuminate the solar cells with one wavelength, and we cause emission in another wavelength, and we just use camera that it's either silicon-based or InGaAs camera that tune to get this wavelength, the specific wavelength that we look for. So for silicon, that's in the infrared range. So we usually illuminate in 800 nanometers, and we collect around 1,000.
so Ziv,
Yeah.
oh, sorry, go on.
So you go ahead, Mark.
Yeah.
I wonder if that's a very expensive process to collect this images.
So it's not, it depends on which technology you use. I call them luminescence images, but there is something that called photoluminescence or electroluminescence. It's not too expensive. As you can see, it's become quite the standard, but the standard use of this standard technology is very basic. And what we tried in this project, and you can see Priya here that joined as well, what we tried is really to get more from these images, because our feeling is our industrial partner collect the information, but don't really use that. And that's the project. We try to see what we can squeeze from these images, except of nice images.
Okay, good. We've had a bit of other people inspired to ask questions now. Pascal, I think you had your hand up first.
Yes, Ziv, I have a question for Ziv. It actually has to do with the data set that you're training. So was it just looking at manufacturing efficiency? Or are you also going to look at also weathered solar panels to see what their efficiency is, to see if your network is good at picking out the efficiency once a solar has been deployed and has been aged?
Okay.
To see. Yeah.
So that's a great question. In this step of the project, we focus on solar cells in companies, just because our industrial partner is solar cells companies.
Okay.
But the next stage, and that stage that we already speak with our partners, is to look on the module. And the module is the part of energy, the part of the system that you see on the roof. And that's usually made by 72 solar cells. So yes, our direction is to go to modules and to go to outdoor inspection as well. But at this stage, we focus on the needs of our partners, that it's in the factory level.
Okay.
All right. I have a bit of a naive question, maybe for Mark. So obviously, Mark, if I understand yours right, the idea of this is you'll be able to adapt HPC systems to run some of this complex code more efficiently. Do you have any feeling for, I mean, what's ultimately what could be the impact of this? Are we talking real significant efficiencies in use of this high-end expensive equipment?
Yeah, some of the cases that I've been working on, we're seeing like 40 or 50% improvement, which is quite significant. The systems use a lot of resources. Like my previous work was on energy efficiency of HPC systems, and some of them use millions of dollars worth of electricity a year, enough to run small towns on. And so any efficiencies you can get often have a huge benefit. So yeah, I think we call 25 or 30% efficiency improvement quite a good success.
I think so, yeah. I see Jingbo here sitting there with the Gaudi sign behind her, and no doubt would be very happy with the 25% increase in capacity of the systems there.
Absolutely. Taking your comments, I actually have another question related to Mark's talk. You mentioned about the performance improvement. Did you apply anything in the real application, like a transformer or anything that is a real application, to get a better sense of how much it means to the real application improve the performance?
I haven't talked about real applications in the talk at all, apart from the future work. But we have started looking at a proxy application, I would call it. Like, it's something the Livermore Labs use for evaluating the new systems. It's called LULESH. It's measuring or simulating shock waves in solids. And, that's quite, another level of complexity above what we've been doing. It's got 25 loops in it, and there are all sorts of different loops with lots of dependencies between the loops. And so far, we're getting about 15% improvement, but the possible improvements is 27 or, approaching 30%. So we're hoping that we can improve the model. And the way we're doing that is trying to find where we've got gaps in the training data that's giving us some inaccuracies in some of the loops in the real world application like LULESH. And we're trying to work out if there's a way we can actually do that systematically too. So we've got a good idea from the training data what the coverage we should expect from that training data.
Am I expecting the similar scale of improvement across different HPC platforms?
Well, our work so far has shown that some systems have better opportunities for improvements than others. So, this is the sort of thing that you might do once just to set the system up with good defaults. And then when a new application's to be deployed, you would do it once with that application to get specific defaults for that application. But we do find there are system configurations that are better than others. So if we can help system admin people get the best general configuration for their system to start with, that would be a good win too.
That would be fantastic. Thank you so much, Mark.
Okay, so Priya, you had a hand up for a question.
Yeah, I have a question to Dan for reinforcement learning. So in deep learning, we look for a lot of data set to train the algorithms. I was wondering if we are about to start a project on reinforcement learning, then do we need to think about a simulation environment where we can train our algorithm beforehand?
Yeah, ideally in reinforcement learning, you need that kind of state action next state workflow. So you need to be able to see how an agent's actions affect the environment. So with like a regular data set, you could be like mimicking, you could train an agent to mimic certain actions if you have like an ideal workflow, if that makes sense.
Mm-hmm.
However, for true reinforcement learning, you would need that kind of feedback constantly based off of how your particular action will affect the environment.
Mm-hmm. Thank you.
Thank you, Ryan, and thank you, Priya. And Fabio, you had a question, I believe.
Yeah, I have a question for Mark, which is essentially follows of what Jingbo Wang asked. So I will not ask you how far we are from embedding your technology in our workflow. But the thing I was thinking about is that adapting such such methodology to our applications, fluid dynamics, shock waves, solid mechanics, whatever it is, it probably needs to gather first relevant amount of data on the simple problem. So have you thought about how to overcome that and collecting more information, not only from the HPC point of view, but also from the applications point of view?
Yeah, our aim is to come up with a complete set of training data that we can show as general for a range of applications. So we're not at that point yet. You know, often when we introduce something new, we do find a gap in the training data and have to introduce some new training data. But the aim is to get to a point and then be able to start assessing the training data to determine, you know, before we've kind of cheated, I guess, and shown it something new and realised it has got a gap, to be able to assess the gaps before, and then show it something new and prove that it doesn't have the gaps that we, you know, the gaps that we're interested in have been eliminated. You know, the idea is that you would use the training data set on a new system once to train the model, and then using only a very small number of runs, 1 or 2 of a new application, you would be able to get the classification for each loop in that application, or the, you know, the pragma class for each loop in that application that's the most efficient. And with Lulesh, we're working with 25 loops, so kind of significant problem there. But you know, there are bigger problems as well, like I guess a weather model or something, that a climate model or something like that would be an ultimate goal.
Yep.
All right. Well, thank you, everybody. I'm aware we are getting into our second half of the session, so we will maybe pause the questions there. I see that Liv and Ryan have already been answering questions in the chat, so I guess if you've got anything else, please pop the questions in there. Mark, Ryan, and Liv, if you can carry on doing that. Mark, Ryan, and Ziv, if you can carry on doing that, that would be fantastic, please. All right, so we move on to our second half of the afternoon, and our speaker now is Amanda Hodgson, who is going to be talking about using machine learning to detect dugongs and other marine megafauna. So, Amanda, if you are ready to go,
okay,
just
thank you.
pop your screen share up and start whenever you are ready.
Okay, just checking that you can hear me to start off with.
Yes, we can. Yes, thanks.
Okay.
Okay, and we can, yeah, we can see a dugong, so you're all good to go. Thank you.
Great. You can't see yourselves, can you? You haven't got this. Okay, good. So thanks everyone. So myself and my colleague Frederick Mayer from the Queensland University of Technology have been working on a way to use machine learning to help support marine megafauna conservation by providing novel solutions to assessing their populations and distribution. So in our case, I'm a biologist who needed a computer automation solution, and Frederick is the machine learning expert. So again, I may have to direct any questions to Frederick, but I can certainly answer any about the actual application of this work. Okay. So just to give you an understanding of why we're doing this and why it's important, I'm going to just focus on dugongs as the example because they were the first species we started this work on and probably the species that we'll apply this work to first. So a key fact that you need to know about dugongs is that they're found in 46 countries throughout the Indo-Pacific. Most of those countries are developing or underdeveloped, but and dugongs are a class is vulnerable to extinction globally and are disappearing largely because they feed on seagrass and their seagrass habitat is disappearing alarmingly rapidly. And we care about that because many countries throughout the dugongs range, well, I guess that's a huge concern to countries throughout their range because the seagrass meadows support half of the world's fisheries and feed 3 billion people. And seagrass is also important as it provides protection against climate change. It provides stability and also absorbs and stores carbon 35 times more efficiently than rainforest. So that's a little known fact. And dugongs are an excellent barometer of seagrass. If the seagrass disappears, so do the dugongs. And they're much easier to monitor than seagrass because the seagrass occurs over vast areas of millions of hectares. And whilst it is sometimes visible from the air, like it is in this lovely photo, usually often it's not. But dugongs that are feeding on the seagrass have to come to the surface every few minutes to breathe, so they can be detected from the air across their entire habitat range at least some proportion of the time. So you can see here there's an example of a mum and calf in this sort of aerial photo. Basically, we want to monitor dugongs not only for the sake of conserving a unique and important species, but also to allow us to track the health of seagrass meadows throughout the dugong's vast range. So for over 30 years in Australia, we've conducted aerial surveys of dugongs, and by that I mean people on board a small plane recording all the dugongs they see as they fly backwards and forwards along set transect lines like the example here in Shark Bay in Western Australia. Hopefully you can see those red lines that represent the flight path, and that's a survey that we do pretty regularly or have done since the 1980s. So for the last decade, I've been developing methods to use drones to replace the occupied aerial surveys because drones are safer, potentially cheaper. We can achieve more accurate and more precise data, and we can fly in previously inaccessible areas. So with the support of In Situ Pacific, which is owned by Boeing, I did a series of trial surveys with their lovely high-end military drone called the Scan Eagle. And with that, we could do the same survey that we do with a normal plane by just using two cameras that are continually capturing overlapping photos along those same flight paths. So in that inset there, each of those rectangles is a footprint of a single photo. I've just highlighted one just so you can see it clearly. And in this particular survey, the total length of all those flight lines is 3,000 kilometres, and the full survey would result in over 77,000 images. In this case, this trial that we did, the images were 24 meg, and they take people on average 36 seconds per image to review and find the dugongs in the images. So one survey image set would take over 700 hours to manually review. So this is where I say that in our effort to sort of use machine learning to detect marine animals, we started, unfortunately, with an animal that's particularly difficult because people might think of detecting marine animals and think of an animal at the surface of the water where you basically just have a blue background and detection is relatively easy, but dugongs don't spend much time at the surface. They're often below the surface and often visible on the sea floor, in which case they're over seagrass beds, which makes the images quite complex. And then they become even more complex when you add glare or murky water, or you have high winds that create some white caps on the water. So to successfully automate the detection of the animals in the images, we want to aim for recall rates that are somewhere close to being as good as people manually reviewing these images. And we've tested the human detections by comparing 3 image reviewers using a Mrk capture model, and found that on average, people detected 90% of the dugongs that were actually in the images. So there's been a few versions over the years of our machine learning solution, which is dubbed the dugong detector. The original version was published in 2015, and in that we compared 2 different deep learning architectures and advocated just a simple segmentation and region proposal method. Frederick then went on to develop a new system using the Google TensorFlow platform. And I tested that system using over 37,000 images that were manually reviewed, which incidentally took 377 hours to review manually compared to 18 hours to verify the dugong detector's output in a really sort of basic and actually quite just laborious way of verifying. So that time would get quicker, I imagine. I included images from the full range of conditions and environments and complexity. And the detector found around 71% of dugongs in images that were obviously naive to the system, so weren't used to train it. That's not as high as I would like it to be. I've always aimed for at least 90%, not just because that's what the manual reviewers can detect, but also because in some cases, the areas that we want to use this system in, animals are occurring in such low numbers that we just can't afford to be missing 30% of them. And now I guess this idea of using drones and aerial imagery for marine fauna surveys has exploded, and there's demand for a system that can detect a range of marine fauna, so that we can use either drones or normal planes as aerial photography, or hopefully in the future, even satellite photos to assess the populations of other threatened species. So Frederick and his team have now created a new system that's trained to detect this range of species, so dugongs, whales, belugas, dolphins, turtles, sharks, rays. It uses an updated version or the latest version of TensorFlow and a efficient depth architecture that can be scaled. So we've at this stage selected the lightest version, which has an input image of 512 by 512 pixels, and you just shift that window across if you have a larger image, that window is just shifted across the image. Unfortunately, this was such a new version. I literally only received it last week. I haven't had time to test this latest version. So for some of the species, we actually have labeled images that haven't actually been used to train that detector. So we're still needing to do a bit more testing and training. And I'm particularly interested to know how well the system does in detecting animals in new environments. So that the system has been trained for dugongs that basically in labeled data that was captured in Shark Bay and Exmouth Gulf here in Western Australia, but we have some images from the Northern Territory where the water is a lot more murky and the conditions, frankly, are often quite rubbish for aerial surveys. So I'm quite keen to see how well it does at finding those dugongs, and then in that sort of naive environment that dugongs haven't been used, that we haven't had training data before from, and see how well it does, because I guess the idea is to see, do we have to have a sample data set to train the network every time we survey in a new area, or is it reliable regardless? Ultimately, the system will still need human verification, so we're still just aiming for something that will detect any possible animal sightings, and then we can do the classification. A high rate of false positives compared to true detections is not a huge drama, because it doesn't actually take very long to do the verification. And as I said, we'd rather the higher false positive rate than to miss any animals. I guess the training data that we do have, I guess ultimately it will be able to distinguish well between the different types of animals, but at this stage it's probably not going to do great at that because of the size of the training data set that we've used. Yeah, I guess I should reiterate that the 71% is a pretty harsh assessment. So for this example, for example, in this image, the detector found these 5 dugongs, but it missed these 10, which are actually quite difficult to find manually. And also, I guess my research has suggested that they're likely to be missed by observers on board manned planes as well. But ultimately, we want this combination of aerial imagery and the detector to be better than our, old version of people on board manned planes. So I guess we're going for gold here. For future work, as I said, we need to evaluate the latest detector. Frederick is keen to train that network based on efficient D7, which has bigger input window. I haven't spoken about deployment, but at this stage, the idea is to deploy the network using a Docker image so that we don't have to worry about whether people have the right operating systems on their computers. And so that's an idea that we're just trialing at the moment. And the detector will be integrated into the image processing software that we've developed, which includes an interface for manually reviewing the images and labeling sightings. And it has a mapping component which automatically maps the image footprint as well as the sightings, and it allows you, for example, to see where you've marked a sighting that overlaps into successive images. And you can export all of those, the footprints and the sightings in various GIS platforms. So it just means that the software we're going to integrate the machine learning component and the verification process so that all of the sightings that are manually or automatically detected will be integrated in the same format. So yeah, the ultimate goal is to make marine fauna surveys accessible to non-experts around the world in communities where, using the dugong example, they want to monitor the health of their dugongs and seagrass beds because that's important for their livelihoods. So the hope is that we can use drones to conduct surveys, and then the processing of the drone images would be as automated as possible to obtain data that's standardized across all of those countries. Thank you very much.
Excellent. Thank you very much, Amanda. So there aren't any questions in the chat, but we do have 30 seconds or a minute if there are any quick ones that anyone would like to ask. If not, I do have one, Amanda. So if you've got like a 20-fold speed up over human calling of your images, and you've got drones, could you take more images from lower heights and take advantage of having sort of higher resolution imagery to improve the call rate? So just sort of throw more data at it rather than so try and get past that 71% call rate.
Yeah, I guess the challenge is always we're trying to cover such huge amounts of area, and it would take twice as long to do that. So the challenge is always that sort of weighing up how long does it take to do the survey. We're trying to sort of capture a moment in time so that we can accurately, count the animals. So if it takes too long to do the survey, there's time for the more movement. So it's a balancing act between those two things. Yeah.
Right, thank you. And one other quick one from Jade. Are there any special considerations in programming the drone?
In terms of what? In terms of
she hasn't specified. Jade, are you there somewhere? No. Okay, we might have to come back to one later on, get a bit more clarification on that one.
Yeah.
Okay. So yeah, there's a couple of questions coming through the chat again. So, and if you're able to answer any of those in the chat, that would be great, Amanda. But we will move on to their next one. So this would now be Fabio Capitanio, who is going to talk for us on understanding earthquake physics and using machine learning for that. There you go.
Can you see my screen?
Yes, we can, Fabio. You're all ready to go whenever you're happy.
Yeah, thanks for the invitation to talk to you. First of all, I'd like to, acknowledge that this is a collaboration, like many others that you've seen today, between myself and my group at the School of the Earth, Atmosphere and Environment at Monash, and the Data Science and AI platform of Monash. That would be my team. So it's the guys at EAE. There would be me and my student, Juan Carlos and Tiagi, geophysicist. And on the other side, we collaborated with Mitchell Hargreaves and two interns, Darren and Ravi, that you probably seen in the first talk today. Okay, so my goal is essentially trying to untangle the mysteries of this of earthquakes, and probably one of these nicest way to show it is showing it like these beautiful starry nights that you can see here. These are just all the earthquakes recorded in since 1898. And earthquakes are obviously, as you can see here, a ubiquitous feature. They occur a little bit everywhere, but most importantly, the biggest and the largest occur around what we call plate boundaries. Plate boundaries is where two parts of the Earth they meet, and this is a classical example of Japan Sea and the Pacific Ocean. One of the two plates is essentially going sliding under the other plate, and sliding across the other plate creates this rubbing, which is nothing else than an earthquake, essentially. So all these little dots that you see here are earthquakes, and this is an example of the Tohoku earthquake in 2011. Point is that these are two realms that you can see there. They have completely different physics. One is the physics of the sinking of the plates into the Earth mantle to depth of 600,000 kilometers down in the Earth. It's a problem that usually solved by means of viscoelastic deformation. Usually we are using a fluid dynamic approach. Characteristic times are between 0.1 and 1 million years. Usually this process, they go on for 100 tens of million years. And the velocity at which these processes occur are quite slow, are in the order of centimeters per year. On the other side, we have the problem of the earthquakes. The earthquakes are a classical example of plastic failure. Usually it's elastoplastic, but plasticity will be a dominant mechanics in this problem. Characteristic times there are in order of 10 to 1,000 years. So these earthquakes usually are recurrent over these time scales. And when they release their energy, they essentially show bursts that they reach up to meter per second. So completely different type of problems that they interact somehow. The problem is that we do not really know how they interact. So while we do have approaches for the physics or the mechanics of one problem and the other, still you can imagine that connecting the two over these two very large spatial scales and temporal scales, it's still quite challenging. Solution to that would be viable if we had infinite computational resources, but we don't. And the shortcoming of not being able to untangle this problem are, of course, needless to say, disastrous, and I will stop it here. So we all know how dangerous could be our lacking of understanding of this problem. Other approaches do exist and have been, of course, applied approaches of artificial intelligence to this problem. Classical example is the one that you see here, which lists all of different type of approaches that have been published in the past. Usually the fundamental data sets is the earthquake catalogs, which contains an order of 140,000 events in the last 100 years. Sometimes also some additional geometrical features of the earthquakes are added in. But this, in principle, is a process that has been tried many other times in different incarnation. But the problem with that is that it remains a purely stochastic problem. It's not really, doesn't really contain the physics nor of the subduction itself or the sinking of the plates, not even of the physics of the earthquakes. So in principle, remains a purely stochastic approach and lacks of a way to explain the observation by meaning of a mechanism. So there was our question. And the way we approached it, essentially, we've looked again into the geophysical observations, and we have selected some that they do have a physical meaning for us. So they're not just purely geometrical descriptions, but they are geophysical observables. They usually are recovered from marine surveys or from satellites. And you can see these are a number of processes of datasets have been reprocessed by Zuhir Mod, one of my students. In the top left, you can see that there are some gravity anomalies of different type of wavelengths, crustal thicknesses, and mantle tomography. I just give you an image in the center, which is quite descriptive. So in principle, all of these combined together, they constrained nothing else than the mass distribution in the Earth. You can imagine that the tomography you see in the center, it's a real tomography. You probably have seen a CAT scan. It's exactly the same that we do with the Earth. On the other side, we also have some other data sets that are relevant to us, but they are relevant because they show what would be the effect of an earthquake. And the effect of an earthquake is, we all know, it's deformation, it's permanent deformation. And the plot that you see in bottom right are just the calculation of the integrated seismic strain over the full catalog of the earthquakes, the historical catalog of the earthquake. Another way, then a way to include the physics in it is basically to understand the physics of these two processes. As I said before, we do have a meaning, a way to understand the two processes together in separate scales. And this is somehow the forte of my group. So the one that you see in the center is a model, numerical model, that mostly resolves the fluid dynamics of subduction. So this is the example of the Southeast Asian plates. So it's the same example of the dataset that you see underneath. And from top of those models, we can essentially recover some features that we think are relevant at the temporal scale we're interested in. The whole thing eventually boils down to the solution among all the many equations that have been essentially thrown away. So we are happy to remain with simply the elastic stresses inside the subduction zone. And the elastic stresses are essentially those stresses that are then released in earthquakes. So we model how the physics of how the stresses are accumulated, are created in the first place in the subduction zones, and then eventually we'll try to understand how they create these stresses. They correlate with their effect, which is deformation over two timescales, the timescale of the single earthquake and the timescale of the full catalog, so the last 50 to 100 million years, according to the quality of the data we want to use. And this is the one that you see here is essentially a finite difference solution to the equation you see on top that I've worked on with my student Juan Carlos Graciosa. So we come to the artificial intelligence part, which is nothing else than a classification problem to start with. Why not? The way we want to do it and the way we think it's the best way to start with is essentially using the classical approach, which is to have a fully connected network that you see here, which has an input layer, an output layer, and a number of hidden layers. In our case, only has 3. We can do an encoding of the magnitude of the earthquakes, which we indicate with MW. And eventually we can come out with some classes that tell us the 3 classes for the magnitude of the earthquakes, so in classes, and another class that essentially tells you a continuous between 0 and 1, which is equivalent of the magnitude of the earthquakes, which usually goes from 0 to 10. Point is that in the classical approach, they would have only used some earthquake catalog. Instead, we thought that to embed into this network the role of the physics is essentially necessary to have a physical model that can create some prediction of what will be the cause of earthquakes, and then a number of physical observations that come from the model that essentially they measure how the deformation in the models is created. So eventually, in a very simple way, we've embedded a number of nodes. Here, the number is just for a purpose of the sketch. Of course, there's a number of nodes, a larger number of nodes in the datasets that we have for all these parameters. In this way, essentially, what we do, we try to train the network to understand the physics or to reproduce something that has a logic in the realm of the observation and in the realm of the model itself, of the physics itself. Okay, so the problem, of course, it's not really in the machine learning approach, but it's essentially in the type of data sets and the data themselves and what we do with them. So the first thing that we've tried so far is essentially gridding all these abduction zones. This is just one, it's South America, as you can see. We have the earthquake catalog, which has some, we project somewhere on top of this gridding, and for each one of these grids, eventually we can also sample the physical properties that we've selected in the catalog, in the data sets that I showed you before. Plus, of course, the same projections or the same mapping on this projection on top of this grid that you see on the left of those parameters that we have calculated with our physical model. So again, this is a grid that has the observation in the form of the earthquake catalog, a physical model, and the prediction of our physical model on the center. The problem, as I said, it's a critical problem in the dataset itself for the simple reason. First of all, there are only 8 regions that have very large earthquakes, whereas there's a number of regions that have a lot of many small earthquakes that somehow introduces some other noise in the datasets. And you can recall the Starry Night image that I showed you at the beginning. So earthquakes are ubiquitous, are everywhere, but only 8, they have very big and relevant earthquakes. The other problem is these very big earthquakes, just because earthquakes, they are measured on a logarithmic scale. You can imagine that the magnitude that is above 7, the number of those, it's orders of magnitude smaller than the total, the magnitude that are smaller. So you can see that you can simply scale by saying that for 10 magnitude 6, we have 1 magnitude 7. So eventually the number of earthquakes that are really big and they really have a characteristic signature that it's easy to detect are only around 2,000 over the total catalog that is 104,405. And 4,405. Of course, we really need to do something with the datasets because it's quite tiny as is. Therefore, we need some strategies for the machine learning itself and also for the datasets. One of the strategies we use is a methodology that is called leave one out cross validation that is similar to the k-fold validation, and essentially is the image that you see on the right. And it's quite simple in a way because it simply implies that for every region, which would be essentially the yellow part here, for every region in all the regions, so in all the datasets, we take all the regions except the specific region that we want to predict, and we use it as a training set, whereas the region itself is used as a validation set. So in this way, we have all the catalog except our specific region to train, and then we can essentially validate on the region. And we iterate this for all the other regions. Another problem that we have, of course, is, as I said before, we do have a very small number of regions that they have large earthquakes, and small earthquakes, they are incredibly dispersed all over the world. So, of course, we have the problem of oversampling and undersampling. So some regions will be obviously oversampled because they feature, the occurrence is much more featured in the data sets, and the large earthquakes that are more meaningful, they are probably underrepresented. So 2 strategies we have. One is categorizing earthquakes in categories that are no earthquake or magnitude 4.5 to 6.5 or magnitude 6 and above, just to reduce the bias. And other approaches that we use is classical approaches of multitask learning. So essentially we combine a regression with a categorical approach to minimize the well, they eventually they will interfere, but will interfere positively. So eventually there will be this learning that is assisted between the two.
Fabio, I'm afraid we are running out of time. So if you can bring it to a halt reasonably quickly, please. Thank you.
Okay, so there will be the algorithm itself, and this is how it works. So essentially, you can see that these large circles are large earthquakes, and we can somehow do a good prediction. Somewhere we can predict the location, but not the magnitude. But the most important part is what we're going to do next. We're going to improve on the data sets, and let's skip. But the other thing that once we've done the classification problem, we can essentially use a layer-wise relevant propagation, this methodology that will allow us to explain which one of the physical parameters we've introduced has a major role in the physics of earthquakes. Thank you very much.
Look at that. Wound up brilliantly. Thank you very much. Okay. Adam has a question there. It's quite a long one. So maybe you can just read it yourself and see if you can answer rather than me reading it out for you. Okay.
Adam, there is a lot of redundancy covariance in the different types of inputs. Fully connect model, physical measurement of location are likely correlated with essentially caused by the physical model. Is there a lot or just a little? And would the model benefit from a lower dimensional input? Yeah, exactly. That's the point. That's the point. So this is essentially what we don't know. So we assume that they're all earthquakes and they all have different magnitude. But the question is, are they all the results of the same physics? We think that magnitude 7 above, they really have features that look like they respond to the same physics, but the other could respond to fluid, cow walking over the subduction zone, injection of fluids, you probably extraction of fluids like water on petroleum. So that's the problem. Not only there is a cross-contamination, but we don't even have an idea on how to untangle that. Good question. And
Thank you very much, Fabio, and thank you for the presentation. So, again, we'll have some opportunity to come back and ask more questions later on, but we will just now get our final speaker for today, who's Chahat Raj, who's there. Excellent, Chahat. And Chahat is going to speak to us about cyberbullying monitoring. So, Chahat, as soon as you're ready, if you'd like to share your screen, and you can get underway. That looks good. All right.
Thank you, Mark. Thank you, Mrk Crowe, for this opportunity. So we are a team of 3, Dr. Prasad, me, and Anna Bharati. So we are the researchers at the University of Technology, Sydney, and my area of research is social media monitoring, and I am involved in researching various social media areas, one of which is cyberbullying.
Chahat, can I just interrupt you a minute? Chahat, can you hear me? Can I just interrupt you a minute? Yeah. Can you maybe turn your video camera off, because the sound is really breaking up a lot?
Yeah. Fine now?
Oops, you've turned off your screen sharing as well. Or you've gone altogether. Hang on. Well, you seem to have this Chahat. Chahat either has a network problem or she pressed the wrong button. Okay. All right. Well, while we try and get her back again, did anyone have any more questions for Fabio? No, we've got a little bit of extra time that we weren't expecting. Oh, no, hang on. She's back again, we hope. All right.
Sorry for the interruption.
That's better. Yeah, we can hear you better now. Thank you.
Okay. So, so as I was saying, my research focuses on identifying social media ailments. So I have been researching into information pollution, fake news, rumors, and cyberbullying and deepfakes. So these are all the social media elements we all face in our day-to-day lives. So the problem is we are not able to identify, and there's no algorithmic tool that can identify these for us. So users have to use their own cognition to identify such cyberbullying or such ailments. So introducing the cyberbullying definition, as we can know, internet and social media are largely accessible around the world, and the motive of online social networks was to allow interaction between people. But since it is being very much overused, and the constitution of various minds and different types of social media users are polluting the internet. So we are very frequently seeing proliferation of poor content quality on the internet, with rise in language. These comments are targeting certain social groups and causing discrimination against a number of people. So this is the current scenario of the internet pollution. So also this has a negative effect on society and their minds, because it causes a mental trauma and issues to their mental health overall, because users cannot cope up with the stress they face in their day-to-day life. So as we can see, that we cannot flag such content, and the social media apps are not able to identify this. We need a tool to automatically identify such content and flag them. So challenges in this domain that is being generated each minute. So the data is huge, and it is really impossible to identify each post or each content that is being updated online. So this is a huge challenge. Also, there's a lack of availability of balanced and labeled datasets, because scraping datasets, because we have a policy that does not allow scraping datasets from various social media platforms like Facebook and Instagram, although we have free Twitter APIs, so that's the only thing we are left with. So there are very few datasets that are manually annotated. Also, this is a rarely new domain, so very less literature is present in this scenario. So our research in this domain focuses on analyzing what AI algorithms are present, and we then propose new deep learning methods and machine learning methods towards identification of cyberbullying posts on the internet. Also, we identify the effects of various feature extraction and text embedding techniques. So how natural processing works differently with different algorithms. So these are the three datasets that we are working on. So the first one is the Wikipedia attack dataset that is scraped through Wikipedia comments. Another one is also the Wikipedia dataset that is about web toxicity. So as you can see from the word clouds, the data for attack and toxic are also very much proliferated with hate speech, while the non-attack and non-toxic are quite simpler sets of words. So this displays the scenario how cyberbullying is so much spread on the internet. Also, all of these three data sets are from 2017. So these are fairly recent data sets. So how first is obviously to input the text data and then pre-process it to make it we're able to allow the algorithms to run. Whether is to 20. These types of feature extraction techniques. We use 4 types of feature extraction for machine learning algorithms. We use count vectorization, which is a statistical technique. Of the occurrences of the word. And for gram means unigram, a single word, the occurrence of a single word. Then we use TF-IDF for bigrams and trigrams. That means the occurrences of 2 words and 3 words as a phrase together. We use TF-IDF character, bigram, and trigram. That is for character. So we have used 4 embedding techniques for machine learning algorithms, which we then feed to these 4 algorithms: XGBoost, naive-Bayes, SVM, and logistic regression for a baseline comparison. Then these are the 3 techniques we used for deep learning: GLUF, fast text, and paragram, which are used for embedding the deep learning techniques. And these are the deep learning techniques that we propose, and we propose a vanilla model for each one of them. and analyze the effects of each feature extraction technique. Then also we propose these hybrid techniques where we combine a transformer block with all of these deep learning techniques and then analyze the effects of how these are performing. So the basic idea of using these, proposing the transformer hybrid approach is that what happens in the normal deep learning is the text is processed sequentially, suppose in neural networks like CNN or LSTM or GRU. The text is processed word by word or sentence by sentence. In transformer, there's an advantage that we can take up the text from anywhere in the entire domain, and the neural network itself identifies which text is more important, and we don't have to go by. So this if you the text and the map we use those things for machine and deep learning. Then these pipelines for the similar.
Okay, unfortunately, yeah, I think Chahat's obviously struggling with network connection where she is. So, yeah,
maybe
sorry about that one.
Yeah, maybe I will add a few comments to what she's working on.
Oh, right, thanks, Anna.
So I mean, she's doing an excellent work in where in this one she has compared both both traditional machine learning as well as deep learning techniques, and evaluating their performance. And so one of the key, I mean, naturally, of course, deep learning techniques are winning hands down. And the level of performance that is seen is quite surprisingly quite good. And in fact, we are seeing actually in almost all the techniques, we are seeing about over accuracies of over 90% and precision and the recall also in the same as well as F1 score in the same range. But of course, this being an imbalanced data set, of course, we don't want to place too much emphasis on the accuracy itself, but even the other metrics appear to be quite good, particularly for the deep learning data set. So chart is back, so I'll let her continue. So I just quickly summarize outcomes, but yeah, so anyway, we have a few minutes, you can continue. Chart, you're there?
Yeah, so shall I continue the presentation?
Yeah, please continue.
Might be best if you just do it by, oh, okay. I was going to say, maybe, can you do it without screen sharing? Because I think that's not helping.
So I just summarize the significance of your results, and then how deep learning is performing well, and the performance is around, I mean, over 90% in most cases. And then maybe, and of course, it's an imbalanced data set. And then you want to also, I mean, not just dwell on the accuracy, but the F1 and so on. So that you can continue from there.
Okay. So as visible from the results, the machine learning based algorithms are performing a bit lower than the proposed deep architectures, and we are able to see that by neural network, you know,
no, okay, just too much there, unfortunately. No, I mean, very, very important and useful topic there, but yeah, Thanks, Nana, for giving us a quick catch up on that one.
Sure.
Yep, I think I have slides, so I can.
Someone's
share the
sharing.
slides
Someone's
and
sharing them.
maybe,
Yes.
Yep. Maybe Nana, you can go ahead and let us know a little bit about the outcome.
Sure. So in terms of the outcome, as if you go to the next slide. So this is all most of the deep learning techniques, as you can see, they are performing well over. They're performing well, and like CNN and BERT and so on. And the machine learning ones are a little behind. And comparing between the data set, the last one, hate speech data set, actually has a good performance. And then similarly, whereas Wikipedia and so on has slightly lower performance. And but it's more. The significance of this is that it's quite. It's not an easy topic, but at the same time, it has a huge significance. We know about roughly 10% of the teenagers are actually have depression or have serious issues owing to the cyberbullying. So this is a topic that needs further investigation. At the moment, a draft paper is being, a manuscript is being prepared for a journal publication. And so that kind of summarizes, but we're happy to answer any questions that you have.
Okay, so are there any questions for Nana or Chahat?
I think I have a question.
Yeah.
Yeah. So with respect to detecting hate speeches or certain words, would you really require machine learning or deep learning algorithm? Because isn't it easier to look at text data as it is and compare the strings to a set of words which might be hate speech?
Yes. Yes and no. Essentially, you could actually have come up with phrases, and that might indicate or that are proxy to hate speech. But majority of hate speech also is in the language, tone, and for example, there can be sarcasm, right, and so on. So detecting sarcasm, for example, is a very hard topic. So that is exactly why you need more in-depth analysis than simply a text processing approach.
Right.
Okay. Especially if you look at hate speech among teenage girls or young women, for example, and that is much more nuanced than that among teenage boys. And so we know boys use A, B, C, D, E, F, G, H, a few words, and mostly maybe centered around F, for example. And but it's not the case with whereas young women have much more nuance, and you also have much the impact can also be significant, especially when it is delivered as sarcasm and so on.
All right. Well, thank you for that. So we got a few minutes left, and I say the intention was we'd come back at this point and have some more general questions and discussion, or go back to further questions for all the speakers from this session, indeed, for the first half of the afternoon. So yeah, just like to invite anyone, if they've got anything they would like to raise, any more details they'd like, please go ahead. I think all our speakers are still here. Certainly Amanda and Fabio are.
There's a question in there about whether some of the dugongs have been tagged and aligning the tagging with the aerial photography and machine learning. I didn't respond to that because it's easier to just speak that response than type it. Yeah, I mean, I guess there's a lot of different aspects of what we're doing, and one of them is finding the dugongs in the images, but the other is understanding the probability of the dugong actually being visible in the first place. So there's been a lot of studies on that in terms of understanding how deep you can see them in the water column, but not necessarily directly related to the imagery. So that's something that, yeah, I'm really keen to do, is just follow tagged dugongs around and understand their, the detection rate based on their behavior, but also different types of imagery. And that would be really useful if we could do that with tagged dugongs, but it's a little challenging logistically, but definitely on the radar.
Talking of radar, Amanda, are you limited to visible light, or do you have imagery in other wavelengths?
We've vaguely tested other wavelengths. The tricky thing with using other wavelengths, I guess, is you can probably detect animals in the water more readily, but actually identifying what they are is more difficult. So if you have dolphins, for example, well, even distinguish between dolphin and a dugong can be quite difficult. So the other limitation is that people have looked a little bit into using infrared and things, but these animals are very well thermoregulate very well. They don't actually emit much heat, so that makes it quite tricky.
Oh, thank you. Okay. Anyone else got anything they would like to discuss? Any other comments in the chat? No. I mean, it's been a fascinating afternoon. We've had some, I mean, yes, there's six talks here about some really important and really important topics, and sort of, very clear applications of how machine learning is going to change many aspects of the world. So thank you very much to all our speakers. Taran, we make this video available and things after the talks, do we?
I think that's all. There's nothing else.
No, yeah. So people will be able to go back and have a look at these videos later on if they want to. You'll share those with everyone. Yep.
I will be sharing the recording and also the questions on the chat. If there are answers on the chat, like I'm going to put them all in one document. I'm going to share it post the event. Yeah.
Great. Well, unless there's any final comments, I would like to thank all our speakers very much indeed for joining us this afternoon. Thank you everybody else for taking part and joining in the discussion. And we hope to see you all at our next one of these. Do we have a date yet, or would you send out information, Darren?
It's sometime next month. There's tentative date, but I can't be like, I mean, if you're subscribed for the ML4EU, then you should get a notification, and then you should see 6 more presentations next month.
Excellent. Well, thank you very much, everybody. Hope you all have a great afternoon. I hope you enjoyed today.
Thank you.
Thank you very much. Bye-bye.
Thanks, guys.
Bye.
Thank you.
Thank you, Mark.
No problem, Darren. See you later on.
See you later.
Hi, everyone. Thank you, Mark. Thank you, Mrk for this invite. So the focus of this research talk is cyberbullying monitoring. We are a team of 3, Dr. Mukesh Prasad, me, and Yana Bharati. We are affiliated to School of Computer Science, UTS, Australia. So I'll introduce myself a little bit. I have been researching into social networks and cyberspace. The focus of my research has been web information pollution detection, and I have researched into cyberbullying, fake news, online rumors, deepfakes, and other social media elements. Coming to cyberbullying, internet, as you know, and social media are largely accessible around the world. And the initial motive of building online social networks was to allow interaction between people, to make communication easy. But with the rise in social media users and constitution of various types of minds and different types of social media people, the pollution on the internet and on the social media platforms has been continuously rising. So we are very frequently seeing proliferation of poor content quality on the internet or on social media, with rise in abusive speech and offensive language and sexist comments and remarks, and people targeting certain social groups and causing discrimination against specific users and specific organizations or specific countrymen. So this is an entirely polluting scenario that degrades the quality of internet usage. Also, it degrades and brings mental trauma towards people and causes them health issues, and overall it pollutes the internet. So also the social media platforms are not in a condition to verify each content being uploaded on the internet. So it becomes very hard to identify such issues in the real time. So coming to the challenges of cyberbullying detection, the content on social media is being generated every instant. Like every instant you see there's a post coming up, and for social media platforms like Facebook and Instagram and Twitter, it becomes very hard to identify which post or which content is malefic. So it is very, so we need some AI algorithm to automatically identify which is an illicit content. Also, there is a lack of availability of balanced data sets and labeled data sets priorly, because we cannot scrape, we are not permitted to scrape Facebook and Instagram data because their API do not allow us. Although we have one resource, that Twitter, so that's what we are left with. And so the most of the data sets available are from extracted using web scraping or from Twitter. And so also the problem has been rising from the past few years, since after 2016. So this is really a very new problem, and literature is very limited in this domain. So also very less frameworks have or AI models have been built up to detect such malicious information content on the internet. Coming to the contributions of our research, we perform a deep algorithmic study analyzing various machine learning and deep learning algorithms, how well they classify on such cyberbullying datasets. And we employ 4 ML algorithms and create 13 deep learning methods, in addition to some priorly established deep learning models, and also introducing novel hybrid algorithms with merging 2 or more deep learning models together. Also, in addition, we analyze the effect of various feature extraction techniques on word or on character content. So we analyze how various techniques perform in combination with the deep learning and machine learning models. In regard to data sets, we have worked on 3 real-world data sets, and all of these data sets are from 2017. First one is the Wikipedia attack data set, scraped from Wikipedia comments. Another one is also a Wikipedia toxicity data set, also scraped from Wikipedia. And the third one is a hate speech and offensive language data set that has 3 categories, in which the first category is about hate speech, the another is not hate speech but offensive language in any sense, and the third one is which is neither. So as visible from the word clouds, we can see that the majority of the comments on these data sets in the attacked section are very much disregarding and disgracing the internet. And whereas those in the common non-attack categories are very day-to-day life used words. So this is the entire scenario of such pollution on the internet. Coming to the workflow that we propose, we obviously first input the text data. Then we pre-process the textual document data and perform these pre-processing steps such as empty row removal and punctuation removal and numerical and URL removals. And we then tokenize and stem the words to their root forms so that the machine learning algorithms can work on them easily. The data sets are split into 3 parts, training, validation, and testing. And the ratio we keep is 60-20-20. And then we feed them to these feature extraction techniques. So these 3 boxes are for 3 different types of techniques. The first 4 techniques are used for machine learning algorithms. So we perform count vectorization, which is a statistical technique which counts the occurrences of words. Then another one is the TF-IDF word unigram. 1 gram is unigram. So it uses the frequency of occurrence and inverse frequency of the words. Also, we use bigrams and trigrams, which means combining 2 or 3 words together in a phrase. And then we use character bigrams and trigrams, which means combining 2 or 3 characters together in a sentence or in a word. So these 4 techniques are experimented on the machine learning models. We use 4 basic models, which are XGBoost, Naive-Bayes, SVM, and LR. So we analyze these baseline models as to how they perform with these techniques. Coming to deep learning, we use 3 types of embedding techniques: glove, fast text, and paragram, and apply these on these types of deep learning models. We propose simple vanilla models for in terms of CNN, LSTM, GRU, BiLSTM, and all of these. So all of these models contain 1 layer of these networks, and then we combine them with fully connected layers, and then we go on. And another part is transformer word embedding, which is used for the transformer-based approaches. And all of these are hybrid approaches where we merge transformer blocks with the above deep learning algorithms and see how the transformers work with these models. So the main idea of using transformers was as in the normal deep learning models such as LSTM or GRU, there's one condition that we have to iterate over the entire text document sequentially. But the advantage of using transformers is that we can skip to any content that is appears to be very important to the neural network. So the approach transformer uses is identifying the most important words contributing in the identification process and then working upon those. So that's the basic idea of using transformer-based hybrid models. So then we test them on the data sets and then evaluate their results on using these 4 matrices. Coming to the proposed architecture. The first step is to embed the textual input to allow the machine to understand the inputs, the textual inputs, into vector forms. So these are embedded according to the algorithm being used. So in this architecture, the first step is to this network describes that whatever models we are using, and we use each model step by step. So one at a time. So the first model that we use is we first send the embeddings to a convolutional neural network, and then the max pooling and ReLU layers, and then these fully connected layers. So this fully connected scenario is same for each model that we use. We have a dense layer with 50 dimension, and then a dropout of 0.25 to reduce overfitting, and then another dense layer which is dependent on the number of classification labels that are present in the data set, and then a softmax for supporting multi-label classification. So these fully connected remain the same for each one of these. Then after trying with convolution, we use a BiLSTM network. Then BiLSTM goes with convolutional network, and BiLSTM is also combined with an attention layer. So what does an attention layer do? It focuses on the specific words having higher weightage in the document, having more importance in analyzing and in classifying in the classes. So another approach that we use are, we simply use these LSTM, BiLSTM, and GRU by GRU models and check the accuracies on these models. Then another hybrid approach is we combine these models with all of these models with a transformer block. So we analyze how these work. So this is the entire scenario of the proposed architecture. Coming to the results, we can see that the machine learning models like XT2, snake-based, SVM, and LR are performing comparatively lower than all the other results. So that's the basic scenario, that deep learning is definitely performing higher, but which deep learning models? See, the bi-directional models such as bi-LSTM here and bi-GRU. So these are giving a stable high accuracy. Also, the transformer models are performing, the hybrid models are performing superior to all the rest of the models. So analyzing the results, we can say that bidirectional and transformer based approaches are giving high outputs on all the 3 data sets. Coming to the baseline comparison, we compare our methods on the 3 data set on 3 different approaches. On the Wikipedia attack data set and toxicity data set, we use these 3 implementations by previous researchers, and as observable, all of the matrices obtained are higher than those proposed by other papers, other researchers. And on the hate speech also, we use the other 3 implementations, and we see that the accuracies and F1 score, precision recall are all higher with our proposed models. So with deciding on which models perform best, we can see that bi-LSTM is performing the best, then attention bi-LSTM. So we can see that bidirectional neural networks are performing pretty well, because there's an advantage that we can move both ways in the neural network, forward and backward. So that provides an advantage to the deep neural network. Also, towards the end, we see that transformer-based approaches are also performing very well. So now arriving at the conclusions we obtained, among the machine learning classifiers, we saw that support vector machine was performing better than other ML algorithms, and TF-IDF, term frequency and inverse document frequency, was performing well with ML techniques. And amongst the deep learning techniques, for the feature extraction, glove and paragram was performing better than fast text. And amongst the models, we see that bidirectional neural networks were performing overall very high. And also attention mechanism was when combined with bi-LSTM was giving good accuracies. So the overall suggestion would be to use hybrid models such as transformers and attention-based models. Also, transformer is basically an attention model, so it all makes sense that we use attention-based models and bidirectional recurrent networks for such cyberbullying identification, as we establish the results on 3 data sets and identify that these were the models performing well overall. So this was the result that we obtained on. And we see that the feature extraction techniques which ones were performing pretty well and which deep neural networks were performing very good. The other researches that we are currently involved in are from varying domains. We are working on financial data, healthcare, security, and social. So these are the examples what we are additionally working on. We are working on stock market analysis, such as cryptocurrencies prices and financial stock prices, and predicting them using deep learning models. And then we are working on disease classification, such as Alzheimer's disease, chest X-ray disease, and plants disease. And then we developed a model that arrived at 94% accuracy. Also, we are working on threat object detection, where we use various computer vision techniques to analyze, to identify various threatful objects. And at last, cyberbullying, that was the focus of this research talk. So we are into developing various models and overcoming various limitations of the existing research. So thank you.